Don't forget to record your attendance. Okay. So yeah, 50 over and counting. I guess I can start now when I record this lecture. Okay, so today's lecture, we're gonna learn about divide and conquer algorithm. I have introduced the divide and conquer approach in our lecture number 2. So I think it should be easy for you. Dean, you want to say something? So the first algorithm we're gonna learn is merge sort. We have learned this, okay? And quick sort, heap sort, binary search, and there will be one little extra called inserting into the tree, okay? But all these algorithms will be used divide and conquer approach. So this lecture is very similar to our week 2 lecture because it used recursive function and okay, so as the revision, divide and conquer approach is the strategy where we divide the work and then we conquer. So for this tutorial, for the sake of the topic for today, I want to allow you to divide the tutorial question and conquer. Okay, so maybe you can discuss T7, 8, 9, 10. Okay, T7 and T8. So you can divide yourself the questions that you want to answer, and then you try to conquer it yourself, and then during the tutorial then you can explain. Okay. So even the methods for us to answer the tutorial question, we will use divide and conquer approach. So this is the exact slide that you have seen in week 2. I'm just going to revise this a little bit. It breaks the problem into sub-problem. And when you break the problem into sub-problem, you need to make sure that the problem has the similar sub-problem. Okay. And then solve them recursively. After solve them, combine this solution to create a solution of the original problem. Okay, so like for your tutorial question, I think there are 10 of them. So it's a problem where of size 10, then you can divide. You can divide into 2 or you can even divide into 10, up to you. And then each of you need to solve the sub-problem, and during the tutorial session, we will try to, everybody will get the solution for all 10 questions. Okay. The same slide. Okay, so the first algorithm that we're going to revise today is the merge sort. So merge sort is a recursive algorithm that uses divide and conquer approach. In merge sort, we divide array into 2 halves until it reaches the base case, and recursively we merge it into the whole solution. Okay. So this is the algorithm for merge sort. I can see that we can separate this into two functions. The first one is merge sort, where we have the Q equivalents to P plus R divided by 2. So this P is like the first array, it can be 0. R is the last index, okay, and then in this case for merge sort it divide by 2. So Q is like the division between the two. Okay, so for line 3 is the left side of the sub-problem, where it is from the P to the Q. And line 4 is for the right side sub-problem. So it is from the middle, which is Q. We already get the Q plus 1 until R. Okay, so these two is called recursive function. This is not a recursive function because recursive function, the definition is it call itself again and again. Okay, for this merge sort, it calls the merge function. So this one is not a merge, a recursive function. Therefore, we have Tn divided by 2, and here is also Tn divided by 2. Why 2 is because over here is the division of 2, and then the whole merge algorithm is order of n. Okay, so when we want to get the time complex, the equation for this, it will be 2Tn divided by 2 plus n. Then we can calculate the time complexity using the 3 methods. What are they? Do you still remember the 3 methods to calculate time complexity for recursion?
Master theorem.
Master theorem. Alright, what's another one?
Substitution.
Substitution and 3. Okay. N power of Ng Pun Kin, n power of 2. I'm not so sure. Which questions are you? Oh, the time complexity. Okay. So for the time complexity for merge sort, if we use the master method way 1, we will get n log n. Then if we use 3, we will also get n log n. This is the similar so this is the similar example that we have learned in week 2. Okay, so using 3, we also get n log n for the merge sort. Okay, so since we have learned about the merge sort before, I'm just going to give you one example for revision. So this is the given array, and we need to divide into 2. So 85, 24, 63, 45 on the left side. So then it will break to 85 and 24, 63 and 45. And it will break until it reaches the base case. Okay. Then after it reaches the base case, it will do the conquer and combine, where 85 we compare with 24. Since 24 is smaller, then we will swap the place. Next, we compare 63 and 45. Since 45 is smaller, then we swap into swap place. Next, we consider, we compare these four number. Therefore, we get 24, 45, 63 and 85. Then we do the line 4. Line 4, this is line 4 and then this line 3, line 4 again. I better don't explain like that. So for this side, right, it does the same thing. Okay. And lastly, when we compare the left and right for us to get the sorted array. So this is the concept for the merge sort. Can we proceed to quick sort? Because I feel that I need a lot of time to explain about quick sort. Merge sort concept okay for you? Okay, Adam say okay. How about the rest? Okay. Thank you. Now let's talk about quicksort. Quicksort also use divide and conquer approach. And for quicksort, you need to remember the key point is pivot. Okay. So for quicksort, we have the best case scenario, where for quicksort we need to sort by choosing the pivot point. So this pivot point, right, is like any number. Okay, so let's say we have like 8 elements in the array, then we can pick one of the element to become the pivot. Pivot can also be randomly selected. So on top of here, in order to pick the pivot, you can add a randomized algorithm to pick one pivot. Okay. So let's say the best case is when the pick pivot is in the middle. Therefore, there is the smaller elements on the left side and the bigger element than the pivot on the right side. So let's say we have array of 1, 2, 3 until 9 and our pivot is 5. So on our right side, it can be like all numbers is not sorted but bigger than or equivalence than 5. And on the left side, also not sorted yet, it can be 5 or below 5. Okay, so this will be the best case because we can solve the left and the right at the same time, at the time of n divided by 2. So this is the algorithm. Okay, again, for this line is to sort the left line, the left subarray, and for this line is to sort the right subarray. So since the quicksort algorithm has recursive function and it is divided by 2 if it is the best case, okay, Divided by 2 is the best case because the pivot is right in the middle. The average case will be like the pivot can be somewhere here or somewhere here. And the worst case I will explain later. So the best case is here got 2, right? 2tn divided by 2 plus n for this function. And then when we calculate like our previous calculation, we will get order of n log n. Don't worry about the algorithm yet. I'd just like to explain about the worst case scenario. So, oh no, typo. So worst case when one side of the partition always has no element. So let's say the pivot in this example is the first element on the right. So when we want to do the sorting for all these elements that equivalents to the pivot or bigger, right? So we need to sort this one by one. So for example, like I said, this one is the left side of the pivot is 0. There's nothing to sort at the left of the pivot. And for the right, like everything inside here need to be sorted yn minus 1 because we exclude the pivot. So when we calculate this, right, tn minus 1 plus n, we can use any of the three methods to calculate time complexity for recursion, then we get order of n squared. So this would be the worst case. Okay, so right now the critical success factor for us to get the best case is to get the pivot right in the middle. But in this algorithm, they do not have that. So I would like to open a question. Let's think of how or an algorithm that we can add in order to always get the best case scenario. Anybody would like to try? Okay, so let's say like F this array. Okay, this is the given array that we want to sort. Manually, when we look at this, which one is the best pivot for us to get the best case scenario? Five. Izan said 5. Desmond said 10. Lim said 8. Desmond said 6. Desmond, not fair. You have 2 answers. 2.
Sri Ahmad.
2, 3, 5, 6. Okay, so it can be they won't really have a best case because there are eight elements, right? So we couldn't really get in the middle. The best, it will be average case 6 or 8. Yes, Lin, Yongmi, 6 or 8. Okay, so in this case, we get the best scenario. So let's say if I add another here 15, we try to make it odd number. So it will be the pivot, the best pivot will be 8. Okay, in this case, because it will be right in the middle. Okay, so how to tell computer to pick 8? So that we always get the best case. You can't? Okay, I accept that. Is there any creative way for us to not really get it, but to get the middle value? Length of list divided by 2. If the length of list divided by 2, right now, it's not the index. If the length would be 9 divided by 2 is 4.5. 4.5 is the index but not the value. Okay, Farhan, choose the center value. Yes, choose the center value. Moi, find the range, max, min, then get the nearest value. Find the range, max and min. Get the nearest value to what? The middle, is it? Farhan, you almost, you got it right. You need to get the center value, not the center index number. Always choose random index. Okay, that is also okay, if we choose random, right? Because random will always get like 50-50. Yeah, Desmond. Max plus min divided by 2, and we still need to add some range, because let's say we divided by 2 but there's no number to that, right? Then get the nearest value, like what Moi said. Then look for the, alright, sort it first, then get in the middle. Okay, we cannot sort it first because this quick sort is for sorting. Okay, so the answer is the combination ideas for all of you. Like Desmond said, max plus min divided by 2, and then get the nearest value that available in the array. Got it? Sorry. Okay, so that this is like one creative way for you to get the best case. Okay, so later in your group project, maybe you can do something like this. But I'm very happy that all of you are able to find solution to this. Okay, can I proceed? So for the quick sort, this is the calculation for using recursive tree. Over at the left is 0 because there's nothing to sort at the left side of the pivot. Okay, And then on the right is always n minus 1 instead of divided by 2. Okay, but the main thing here is we want to learn about their idea in quicksort. Okay, the more that we learn on how other people try to solve, I think it gives us more knowledge for us to explore within our area. So whatever existing that they have, we can try to improve it by looking, okay, what is the best case, and then is there any new algorithm that we need to add. Okay, so let's say for this example, I don't use randomize. Okay, I purposely want to do it the worst case, where I always pick the leftmost. If you pick the rightmost, is also worst case. Okay, but in this example, leftmost item is always the one to be chosen to be the pivot. When I look at the algorithm, I sum up 5 key points for you to remember when we talk about the quicksort. Number 1, pick any item in the array to be a pivot. Okay, in example, we take leftmost. And then later there's like comparison, which I will explain later. But for the second key point, if swap happen, I and j will move. I and j is the index. If no swapping, then only j will move. When I say move is j plus 1. Okay. Then, because j will keep on plus 1, so j keep on moving to the right from the left. So when j ends, we need to swap the pivot with I. Then we need to recursively sort the left and the right subarray. Okay, don't worry, I will display this throughout the example. So now the given array is 6, 10, 13, 5, 8, 3, 2, 11. Okay. In quicksort,
gosh.
if you look at the quicksort algorithm, the initialize I is 0, j is 1. For this example, we pick the leftmost as the array. So we can see here, right, pivot is here, pivot and I share the same value because I has not moved yet. Okay. So we already do the first key point to pick a pivot. Next, we do the comparison. When we want to do the comparison, we need to compare the value of j with the pivot. So the value of j is 10, the value of pivot is 6. The algorithm given is 10 smaller than 6. Is aj smaller than pivot? No. Okay, so aj is no. So if no, right, there won't be any swapping. Okay, let's take a look at our key point. If no swapping, it only j will move. No swapping, so only j will move. So right now, I is still equivalent to 0, j is plus 1. So j leaves I. Okay. Then next, we have not reached to key point number 4 yet because j ends. J ends means j is being kicked out from the array. Okay, when j is over here. So at the moment j is still here, so we need to repeat 2 and 3. Over here, I just copy to make this as an answer. Then we compare. Is AJ smaller than pivot? Is 13 smaller than 6? No. If no, again, there won't be any swapping. So what happened?
J plus 1.
J plus 1. Okay, good. Next. J already 3. Okay, J plus 1. Then, again, we repeat. AJ is smaller than pivot. Is 5 smaller than 6?
Yes.
Okay, if yes, what should we do now?
Move I and J.
Okay, good. So we need to before we move I and J, we need to do the swapping first. Okay. According to quicksort, their idea is we need to swap the AJ with I plus 1. So this 5 will be swapped with 10. Become like this. Then we do like what your friend say. We need to move the I and J. See? Okay. Next, can I have one representative? Okay, let me pick one name. Daryl, can you? Is Daryl here? Daryl not here. Izlan Zulfikri, can you help me?
Yes, doctor.
Okay, so now what happened?
Compare I with J, and since J is smaller than I, there's no swapping, so only J will move
Okay,
and I remain.
okay, almost there. We don't compare I and J. We compare J with the pivot. You see here? Can I
Okay.
try again? Okay, re-explain again. Hold on. Okay, over here.
Compare J with pivot, and since J is not smaller than pivot, so there will be no swapping with I plus 1, so J will move forward, increment.
So only J will move. So next J will be?
Number 3. and I remains 5.
J will be what?
3.
Why 3? Because now J is 4, right?
Oh, J becomes 5.
J will become 5 and I will become?
Still remain 1.
Remain 1. That's very good. Okay. Well, at this time, you already know what quicksort is. Just gonna repeat it. Okay. Can I have Goh Yu Zuan to help us? Goh, are you there?
Yes.
Okay. So what happened now?
Compare the J with the pivot.
Okay. Compare the J with the pivot.
And then the J is smaller than the pivot, so I plus 1, J plus 1.
Okay. If J is smaller, then we need to do the swapping, right?
Yes.
Okay. What to swap with what?
Swap the I plus 1 with the J.
Very good. I plus 1. The value of I plus 1 will swap with the value of J. Okay, so 3 will be swapped with 13. So you will just repeat like this. Do you want me to continue or you can skip? Do you want me to continue because it's just going to repeat until J ends? Okay. Islan said no need. Okay. Anybody who wants me to explain until J ends? Okay, quite clear. Sorry, I'm eating. Okay. Farhan say yes. Okay. So, okay. So right now, because it swap, see, if it swap, then J and I and J will move. So I will become 2, J will become 6. Then we repeat back. Now we check if the value of J is smaller than the pivot. Is 2 smaller than 6? Yes. If yes, then we need to swap it. We need to swap the AJ with I plus 1. When we swap it, so when we swap this 2 will become here, this 10 will become here. After we swap it, I and J will move. So just now I2 J6, right? That's why it becomes I3 J7. Okay, then we compare J and the pivot. 11 is smaller than 6? No, 11 is bigger than 6. So, no swapping. So, since there's no swapping, only J will move. Okay, this time J will leave I. So, when J move, right, J got kicked out from the array. we finally reach the key point number 4. When J ends, then we need to do this. So here J already end here. We need to swap the pivot with I. So Farhan, which value that we need to swap?
Yes, Doctor.
So now J has ended. So we
Yes.
need to swap the pivot with I. So which one do we need to swap?
Swap pivot become 2.
Okay. And then over here will become 6, right?
Yes.
Alright. So pivot does not become 2.
Or pivot stay.
Pivot will,
6.
yeah, it is still going to be
Oh,
6. They just swap places.
okay,
Okay.
okay.
Alright.
Understand?
Okay. So right now we have swap it. You notice that the pivot will be somewhere in the middle, and you can say that for the first round, you see on the left side all smaller than the pivot, on the right side all bigger than or equivalent to pivot. Can you notice that? You notice that?
Yes, yes.
Okay, good. So right now we have the left subarray and the right subarray, where we need to recursively sort the left and right subarray using quicksort by repeating from step 1. So pick a pivot. So right now we try to solve left subarray using the exactly same concept. Okay, so 2, 5, 3, how to solve this pivot, right? I can say the X pivot, right, is already at the right place. Okay, the one that at blue color is already at the right place. Okay, so we do not need to sort this. We need to sort the one that is still in green. So 253, 253, 253, and because I choose my pivot, I choose the leftmost. Okay, it's not necessary to put leftmost. You can choose in the middle, you can choose here. Okay, but in this example I choose 2. Right now we do the exact thing. Okay, I'm just going to explain about the left subarray. The right subarray is also the same thing. Alright, so I choose 2 as the pivot. Then as usual, for quicksort, it initialize I to 0, J is 1. So I is here, J is here. So if AJ is smaller than pivot, is 5 smaller than 2? So no, right? Since no, we do not need to do the swapping. So only J will move. Therefore, J will become here. And then we do the same thing. AJ smaller than pivot. Is 3 smaller than 2? No again, right? So no need to swap. So no need to swap. Only J will move. So what happened here? When J moves, nobody gonna help me? Tak apalah, nobody want to help me. So J ends. When J ends, what we do is to swap the pivot. Oh, thank you. Swap the pivot with I. So, you see, they want to swap the pivot with I. So the pivot and I, is it the same thing?
Yes, same.
Yeah. So to computer, right, they do the swapping. Okay, they do the swapping. But in our eyes, it's like nothing really happened. Yeah, yes, Lynn. It's the same spot. That is why. So now, after they do the swapping, we know that 2 is already at the right place. Because when it reach until this, right, step number 4, right, we know that pivot is already at the right place. So now 2 is already at the right place. Therefore, we need to do number 5 to recursively sort the left and right subarray. In this case, there's no left, right? Yeah, then we need to assign new pivot, Mahin. So let's discuss. Okay, yeah. So we want to sort the 53. So now it's sorted. Can you see the new array? This one not yet on the right. Just now it was so 2 we confirm is already at the right place. Then we do the hold on, yeah. Please forgive me. Okay. We will do the right subarray. 53. So we choose a pivot.
Okay, close
like Mahin
again.
said. I choose 5. You can decide to choose 3, up to you. Then we do the same thing. AJ is smaller than the pivot. So is 3 smaller than 5? Yes. Okay. So swap I plus 1 with J. What is I plus 1? I plus 1 is here, right? And J is also here, right? So computer, they do the swapping, but you know, there's nothing that we can see in our visible eye that 3 swap with 3. Okay? Understand up to here? Why there's no changes between here and here, right? Because I plus 1 and AJ is the same index. Okay, so swap happen. If swap happen, what happen? 2 or 3?
2.
2. Okay, 2 means I and J will move. So I will now follow J. When it moves, it reached to key point number 4 because J ends. Okay, what happened when J ends? They swap the pivot with I. So right now I is 3, pivot is 5. So they do the swapping. Okay, and then I'll re-upload this. Please forgive me. So now 5 is already at the right place. Okay, then it reached the base case. Because for divide and conquer, we are actually dividing and conquering. until it reach the base case, which is I think n equivalent to 1. Okay, so now n equivalent to 1, there's no way we can break this element into half. Okay, therefore we get that the 5 and 3, they will switch places. Okay, so we get 2, 3, 5, 6 half sorted array. We have sorted this. So this, the right sub array is still unsorted, and you can use the same way. And can you share your answer with me so that I can update my something like this, so that I can update my slide. Okay, so you can try yourself. I have it in handwriting. Okay, quick sort. Do you like quick sort better or counting sort? Because some of you say that counting sort is like you describe it as magical. How about quick sort? Which one do you like?
Counting.
And he helped this kid out who was selling
counting.
food for his family. And he said, take it
Okay.
to your family, then
So in
spin
terms
it.
of
Later,
the
he
time
proceeded to
complexity,
stop his
counting
bus
sort, quick
and
sort,
come
which
back
one is
out to
better?
see a kid who was crying to see him.
The question is quite confusing. Yeah, because it's like calling itself, right? Bubble sort. You like bubble sort better. Why is it called quick sort when it's so long? Good question. So, Mahin, what name should we put this? Radix. Mahin? You can, I'm not so sure why they call it quick. I see the time complexity. What was it? Because just now we did worst case scenario is n square. So it's kind of, I think counting sort was better, right? Does merge sort having worst case condition too? If you can compare with quick sort, which one is better? Okay. When we talk about best case or worst case, right, there are two things that we can think about. One is the condition of the input. Let's say the condition of the input is like 100% sorted. Then it can be the best case because we do not need to do the swapping. Or the worst case can be the opposite to that. For let's say for the merge sort, I couldn't recall any best case or worst case other than the input condition because it's always divided by half. Why? Not all algorithm has best case and worst case. I mean, apart from the input condition. So, that is quick. Okay. Now is the heap sort. I try to, in order for me to explain about the heap sort, I realized that I need to explain about the heap first. And then I realized that I also need to explain about the MaxCP5. So next algorithm is heap sort, but we are going to learn about the concept of heap. So heap is a tree-based data structure. Each node of the tree correspond to element of the array. So let's say just now we have the element in here. Like in our quick sort, our element was 2, 3, 5, 6, 8, 10, 11, 13, right? So they are like 8 elements. So it corresponds to the node. So it will be like 2, 3, 5, 6, 8, 10, 11, and 13. Okay, so this is heap. In order to build heap, we need to insert the element of array top to bottom, left to right. So that is why it's index 1, 2, 3, 4, 5, 6, 7. So in this slide, I just want to explain about the terminology in heap. The first terminology is root node. Root node is the first node, which is at the top of the tree. Okay, and other than this, including the root node, we call it nodes. So for this example root node, we have the left and the right. So for index 2, the left is index 4, the right is index 5. So usually later in the algorithm, when they say L means left, when they say R is right. Okay. So this is right, and then this is also right. This is called index. And one more important thing about heap is the height. Okay, depending on the number of element, so the this would be the height. So the height will start from 0. This is the root node with the height of 0. So for heap, there can be 2 types. So for this, right, is a complete field tree. A complete field tree means the leaves are completed. Okay, and we also have like another one is partially filled tree. So the lowest tree can be partially filled from the left to a point. So you see here is not filled. Okay, so you have to remember that to build a heap, it will be again top to bottom, left to right. So 1, 2, 3, 4. You cannot put 4 over here. Okay, it needs to be from the left. So that's the terminology of heap, whereby each nodes of the tree correspond to the element of the array. Then I would like to explain a little bit about max heap and min heap. For the min heap, the root node must be the minimum among the key presented of its children. So 10 is the smallest number, and then you see 15 and 30 is bigger than 10. Then even for this 40 and 50 is bigger than 15. 140 is bigger than 30. So this is mean heap. In order to call the entire heap is a mean heap, right? Each of the groups of leaf needs to comply with this rule. Okay? The parents must be smaller or equivalent than the children. So let's say this is 10, this is 10. This can also be complied because it can be equivalence. The opposite to max heap is the root node must be the greatest value compared to its children. So you see here 100 is bigger than the 40 and 50. 40 is bigger than 10 and 15. 50 is equivalent to 50 and also bigger than 40. So this is max heap. Okay, min heap, max heap. Okay. Then I just gonna give you for the max heap or min heap, it doesn't matter if the right or the left is bigger or not. Okay? Up until max heap and min heap, right? We don't sort these two. You see here 10, 15. Here is 50, 40. Doesn't matter. Okay? As long as the parents is bigger than the children, then it's okay. As long as for the min heap, as long as the parents is smaller than his children, then it's okay. Okay? Next. We have not gone to the heap sort yet. Just go one by one slowly. Right now, in order to build a max heap, we build the max heap from the heap itself. Okay, so this is the algorithm to build the max heap, to make sure that the parents is always bigger than its child. So this is the algorithm. Over here is not the order of n because it is divided by 2 down with 1. So it's not even the order of the A length. Okay. So we can consider, although this is iterative, right? We consider this as not up to n. So to be accurate, maybe you can say n divided by 2 or something. But in this course, in this book, they say it's order of 1. So when we calculate this, the max simplify is order of log n. Okay, let's have one example to build a max heap. The first, so max heap, the parents node always greater or equivalent to its child node. Okay, give me 2 minutes. I need to be away. Okay, I'm back. Sorry. Okay, so for us to do the operation of max heap, the first step is to build the heap first. Okay, for us to build the heaps, like I said, it will be top, bottom, left to right. So this is 5. 5 will be the node, the root node. 3 left, 17 right, 10 left, 84 right, 19 left, 6 right, 22 left, 9 right. So these 3 and this array correspond to each other. Alright, the question here, is this a max heap? Somebody? No. Okay. No. Right? Why is it no? Because we can see here, right? If for this, right, 17 is smaller, and like the biggest is 84. It's not even at the top. Okay. So this is not max heap, and it's not even min heap. Okay. So because it is not max heap, we need to call a function called max heapify. Okay, this max heapify is this one. Okay, this algorithm. For a start, this is the algorithm where the A length divided by 2 down to 1. So they want to know what is I. A length is how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. A length divided by 2. So it will be 4.5. So we take 4. So now I equivalents to 4. Index 4. 1, 2, 3, 4. So we'll be looking at this 3. Next, we check. Is 10 bigger? Is 22 bigger than 10?
Yes.
Okay, yes. If yes, then we swap it. Okay. So once we swap it, our array changes. Okay. This is our original array. The 22 was here. But now 22 is here, 10 is here. Why? It's 5, 5, 3, 17, 22, 84. I lost my cursor. 84, 19, 16, 10, and 9. Because we need to read the array. We need to read the array like this. So we have the new array. Right now, because this is a divide and conquer where they use the recursive function, right? They will call itself using the new array. So the new array is no longer here. When it calls itself again, it will provide this array. Then I will minus 1. Just now I was 4, right? So when they recall itself, this A is here, I is equivalent to 4. Then they repeat. Okay, so let's so now I equals to 3, index 3. We have 5, 1, 2, 3. Okay, then you will check. Is 19 bigger than 17? The answer is yes. So they will swap it. Then it will check, because I 3, right? Then 3 divided by 2, so is 1.5. So this is array 1, this is array 2. So we do the is 84 bigger than 3, then yes, then we swap it. And then after that I equivalents to 1, then 84 is bigger than 5, then we swap it. Okay, then we will repeat, because is this max heap? Is this a max heap yet? Not yet. Okay, so it's, if not yet, right, it will continue. You can follow this step one by one. Okay, I'll give you all the arrows. Okay, so it will change until at one point it will become, oh sorry, a max heap. Okay, so so looking at the heap, we find that all parents' nodes are greater than their respective children node, so we have a max heap. Okay, next. Okay, so that's all for the max heap. But this max heap, right, is still not heap sort yet. Okay, for heap sort, we need to add another 2 more steps. So, okay with the max heap? Okay. So, for the heap sort, they added one more algorithm. So, just now we were doing this and this. So, they added one more algorithm, order of n. So, when we plus all, right, the heap sort is the order of n log n. Let's take a look what is this heap sort all about. So, when I try to analyze it, I realized that for the heap sort, we just need to remember 4 things. First, build the heap. The one that top to bottom, left to right. Build the heap, like we did just now. And after we build the heap, we will need to check, is it max heap or not? If it's not max heap, then we need to max heapify the array. Okay, this one also we did in our previous example. Then another 2 key points here. We need to swap the first node with the last node. And then lastly, we need to minus the A length minus 1. So usually the last node, right, later we consider it as sorted, so for the next iteration we can exclude the last node. The concept is, when we do the max heapify, the first node, which is the root node, will be the greatest number, right? So this greatest number, they put at the last node of the tree so that it will be read last. Therefore, we do not need to consider, because we know already 10 is the greatest given this array. So let's take a look at. So after that, we need to do the iteration until the base case. Okay. So I have shorter example here.
Today we're going to learn quick sort.
Given array 4, 10, 3, 5, 1. The first key point is to build the heap.
A pivot is simply one of the items in the array that meets the following three conditions after we sorted it. First, the pivot is in its correct position in the final sorted array. This means that all items to the left are smaller and all items to the right are larger. Let's look at an example. We're asked to sort the following array. Let's choose a pivot. I'll explain the best
Hello,
way
can you
to
hear
do this
me?
later, but for now, let's just choose 3. First, we need to pivot the array
Okay.
to get it out of our way.
It's raining quite
Next, we're going
heavily.
to look for 2 items.
So
Item from left, which is the first
okay.
item starting
So
from
the
left.
first step is
That is
to
larger
build
than
the heap.
Second, item from right,
4,
which is the
10,
first
3,
item starting
5,
from right.
1.
That is smaller than our pivot.
Okay. Then
Starting at 2, we can see that 6.
okay, so we have done the heap. So is this a max heap?
Now starting at the right, we see that 1 is item from right.
No, doctor.
No, not
Let's
yet.
swap
Okay.
item from
So
right
if it's
with
not
item.
right, then we need to maxify the array.
We repeat the process.
Second step.
This time, 5 is item from left, and 0 is item
Okay,
from right.
again, for us to maxify, it will be
Again, we swap.
a length divided by 2. So now we have 1, 2, 3, 4, 5. 5 divided by
One more
2
time.
is 2 and a
This
half.
time we see that item from left
0,
has a greater index. than
1,
item
2.
from right.
So we take
So we
2.
know we're done.
Okay, so we take index 2. In here,
We swap item from left with our pivot.
we can see that it is already max heap, right? So there's no need to do the swapping
Our
because
pivot
10 is
now is
bigger
maximum.
than 5
To prove
and
it, let's
1.
review our 3 conditions.
Okay, so
As you can see, all items
index
to the left are
I
small,
become divided
and all items to the
2
right.
divided by 2, I will become
We said
1.
quick sort is recursive.
So
Let's go through the
we
process
will
one more time.
compare
We
this.
just made.
So over
We'll
here,
choose 7 as our pivot and move it to the end.
10 is bigger than 4, right? Therefore, we need to
I'll let you watch without voiceover.
swap 10 to 4. Okay, so now we have, here is max heap. But because of this, right, do you notice that this node is already violating the max heap condition? So that is why if you follow the algorithm, right, after they swap all on top, right, they will repeat back the iteration.
Now we
Okay,
have 3 and
So,
7 in their correct position.
this 4,
I think you understand the concept. So we'll let
we will
recursion
consider back this, and we will swap the 4
One
and
important
5.
question is how do we choose the pivot?
Then this
This makes
is
a
max
large
heap.
difference in the performance
Okay,
of the algorithm.
because the parent's node is always greater or equals to its child node. 10 is bigger than 5, 3, 5 is bigger than 4, 1.
One popular method
So
is
since
called
we have the max heap, we
This
can
method we look
proceed
at
to
first,
step number
and
3,
the last
which is to
element of the
swap
array.
the first node with the last node. First node
We sort
I
them
can
properly and
is
choose the
here,
middle
right?
item as our pivot.
So this is 10.
We're making the guess
We
that the
and then
middle of
we
these two
swap it
should
with
be close to the
1.
median of the entire array.
Okay.
And as you can see, it's not too far off. Here's the
So
pseudo
when we swap with 1, then it will become like
Quick
this.
sort has the worst case time complexity, the big O of n
Okay,
squared.
just now 1 and
But
10 we
if
swap,
it is
right?
chosen properly, it
So
can be shown to have an
If,
average case. big O.
it will 10 will be at the rightmost. Step number 4 is a length minus 1. Therefore, the next iteration, right, they don't consider, they exclude the this from the recursion. Okay, So the array, the new array is 1, 5, 3, 4. Then after we do number 4, right? Then we repeat back key point number 1. So we have 1, 5, 3, 4. How come I don't hear anything? I don't think. Are you there? You're quite quiet today. Are you? Let me see.
Sorry?
Oh, you're here. Okay, Ting. Help me to explain the second iteration.
Second iteration.
Up to here.
Right. Let me read the slide for a while. Okay, sorry. So these are after building the mass min heap, is it? No, mass heap. No.
Not yet.
Step 1, build mass heap, is it? Okay.
We need to rebuild the heap.
Step 1, build a heap. But we need to build the heap, then we can sort. But why in this sorry, in this example, sorted so next iteration exclude 10. Oh, okay. All right. Okay, I get it. Okay, so after this, we exclude 10, so we check again this heap. So we need to heapify it. So heapify it, we need to check from top. All right, so we check you can see the 1, 5, and 3. This 3 node actually is a triangle. All right, so heapify means that we try to compare the parents with the left child node and the right child node. So in this example, 1, 5, 3, the maximum value is 5. So the left child node is bigger than its parent node. So we heapify means that we swap exchange the value between the parents nodes and also the left child node. All right, then, but we still didn't stop like there. We need to continue heapify the sub-tree. Here, sub-tree means that the heap tree, which indicate, the heap tree of the exchanged left node. So we need to check again the 1 and 4, right? The leftmost heap tree. All right, so we heapify again means that we exchange the value of 1 and 4. All right, so then this we get a mass heap. Right, so we continue to sort means that we exclude the largest or the parent node 5, then we sort with the last element. All right, sorry. Oh, end already, is it? Easy? That's it, easy? The example, this is the mass heap. All right, so after that, we start the sorting, means that we exclude we take out the largest node, or the parent node, which is 5. We take it out and we swap with the last. We put it at the I can say the second last array, means that we swap with the 1, right? The largest node swap with the 1, the leftmost nodes, child node. All right, then we continue to repeat the heapifying step. All right. Okay, so now the array will be 1, 4, 3, 5, 10. So now we need to heapify 1, 4, 3. So imagine 1 is the largest node, then the left child node is 4, the right child node is 3. Then we do the heapify. Alright?
Hold on, ah. I think I got one mistake here, right?
Yeah.
This is one, right?
Yeah.
So after that we need to do the same thing, right?
Yeah.
For this. Okay, thank you so much.
Welcome, Doctor.
Okay. So I hope some of you who may not understand how I explain, you can understand how your friend explanation. Okay. So basically, we just need to repeat that until we will get all this sorted. Okay. So these are the steps. So that is HIPSOID. Okay, so the concept is quite clear, where of course when we heapify, the root node will become the biggest, so we switch this to the last one. So of course the last one will be the at the rightmost of the array, and then the next time recursion, we don't consider the biggest, the largest number. Okay, so that's how they do the sorting. Okay, Mahin, do you like heap sort? Mahin not here. So how do you find heap sort class? Do you like it? Do you like the idea?
Yes.
Okay, quite simple. Okay. So, we finished talking about sorting. Okay, so right now we have learned a lot of sorts, and some sortings are good for different circumstances, and then some of them hybrid with existing algorithm. So I hope that this will make you realize that there are a lot more limitations that you can improve. Okay. So let's move to binary search, because in week 2 I did mention something about the book, okay, where we want to do the searching. When we try to do the searching, we can do some exclusion. Okay, so for binary search, right, we assume that we need to sort first everything, then only we do the searching. Okay, so for example of the book that we learned, this book is already sorted in alphabetical order. Then when we do the searching, because it's already sorted, we can exclude some of them that we feel is not within the range. Okay, so this is how the binary search works. Okay, this is the algorithm, and how we get order of log n. I tried to use the master theorem, but the most important thing I want to tell you, the concept of binary search. Okay, it's very simple. For example, we see here is an sorted array. Okay, so we want to find the value the value 10. We want to know what is the index of the array that hold the value 10. Okay? So right now, step there, I can see that there are only 2 steps. Okay, it still use the divide and conquer approach. First step is binary search, compare the target value to the middle element of the array. So we put n divided by 2. So right now 1, 2, 3, 4, 5, 6, 7. There are 7 elements, and we divide by 2. So it will be 3 will be the middle value. So at step 2, we see that the middle value is 4. So right now our x is 10. So since x is bigger than 4, then we need to search the right half. Okay? So we can exclude this. Next, we have a smaller sub-problem, 10, 40 and 44. So again, we repeat. We take the middle value, which is 40, and then step number 2, since 10 is smaller than 40, then we search the left half. So in this case, it will perform the recursion until it reach the base case. So now it's already the base case. Okay, we can't divide this any longer. So we know that, okay, we have found the 10. And we know what is, then we try to search the index of 10 from the original array, which is 4. So the position of x is at index number 4. So it's the same concept with the phone book. At first we have the whole book, and then we want to search the Z, the phone number that start with the Z. So we divide into half. Oh, sorry, let's say A. Okay, we divide into half. So we know that, then we compare. So maybe here can be M. Then we know that A is earlier than M. That's why we can exclude all this. Okay, and then okay, A is still not good example. Let's say I. So we know that we try to search this, and then we know that I is somewhere here. So that's the concept of binary search. In your opinion, how can you improvise this? Because it keeps on dividing to half. It's not necessary that we just need to divide into half, right? It depends on the situation. So that is like another thing that you can consider. Even when you want to adopt this binary tree, you need to look at the nature of your problem. Okay, so you can, it's not necessarily that it needs to be divided by 2. All right. So okay with binary search? Okay, this one is additional because I do not want you to think of recursion is just for sorting, just for searching. So we try to find something else. Okay, we can also use the recursion to insert to do the insertion within an array. So let's say we have this array, okay. We have this array. Is this a max heap? Is this a max heap? Okay, we have a max heap, okay, and we want to add a new element inside the array. So there is one max heap insert algorithm, okay. But over here, I just want to give extra examples, so I don't describe about the algorithm in here. The concept is we have the 17, 15, 11, so you need to build the heap first. And of course, it's already max heapified because this is max heap. So what you need to do, if you want to insert, this algorithm, they put the infinity at the end of the element, the last array. And then after that, because this element, they want to add 12 into the array, so we put 12 here. Then we max heapify it. Yeah, that's all. Then we just max heapify it. So here it will be 12, and then 12 is bigger than 11, so we swap places. Okay, that is for the max heap insertion. There are a lot more for you to venture, so I hope that you will enjoy divide and conquer approach. Okay, class. So thank you for your attention. Assalamualaikum.